How's everybody doing today? How's the internet connection? Okay, did anybody have any questions for us to get started with? I don't remember exactly where we left off yesterday, so I thought we would start with problem number 13. It says you have a key ring with 5 keys on it. One of the keys is a car key. What is the probability of picking that key? Well, the probability of picking the car key is the number of car keys divided by the total number of keys. And so we have 1 divided by 5, which is 1/5. Part B says 2 of the keys are for your apartment. What is the probability of selecting an apartment key? The probability of getting an apartment key is the number of apartment keys out of the total number of keys, so we get 2/5. Part C, what is the probability of selecting either the car key or an apartment key? The probability of either a car or apartment key is the number of keys that are either for the car or the apartment out of the total number of keys. So that gives us 3 out of 5. Part D, what is the probability of selecting neither the car key nor an apartment key? This probability is the number of keys that are neither for the car nor the apartment out of the total, and so that will give us the probability of 2 out of 5. For problem number 15, it says, what's the probability of getting yellow on each of the following spinners? So for this one, part A, it says all 8 sectors are equally sized and shaped. So the probability of selecting yellow is the number of yellow sectors out of the total number. And we can see that there are 3 yellow out of 8. And so that probability is 3/8. For part B, there are 6 sectors that are equally sized and shaped. So the probability is the number of yellow out of the total, and there are 3 yellow out of 6 sectors. So that gives us 3/6 or 1/2. Problem number 16 says, a die is made that has 2 faces marked with 2s, 3 faces marked with 3s, and 1 face marked with a 5. If this die is thrown once, find the following probabilities. Part A is getting a 2. The probability of getting a 2 is the number of 2s out of the total number of faces. And so that is 2 out of 6, or 1/3. The probability of not getting a 2 is going to be the number of faces that don't have the number 2 on them out of the total number of faces. And since there's 6 faces, and 2 of the 6 have a 2 on them, then, oh, the audio keeps cutting in and out. You're only hearing bits. Okay, thank you. All right. Hang on just a second. Okay. Give me just a second, guys. All right, is that better? Is that any better now? Good. All right, thank you. Do you want me to go back? Okay, we'll just keep going from here then. Okay. Okay, so number 16, a die is made that has 2 faces marked with 2s, 3 faces marked with 3s, and 1 face marked with a 5. If the die is thrown once, find the following probabilities. Part A, getting a 2, and that's going to be the number of faces that have 2s on them out of the total. We know that 2 of the faces are marked with 2s, and there's 6 faces altogether. That's 2 plus 3 plus 1. So 2, 6, or 1/3 is the probability of rolling a 2. For part B, not getting a 2, we're going to put on top the number of faces that don't have 2s on them. And since 2 of the 6 faces did have 2s, that means 4 of the 6 faces will not have a 2. So the probability is 4 out of 6, or 2/3. For part C, we want to find the probability of getting an odd number. And the probability of getting an odd number is the number of faces that have odd numbers out of the total number of faces. And there were 3 faces that were marked with a 3 and 1 face marked with a 5. So that means there's 4 faces that have odd numbers out of the 6 faces. So that probability is 4, 6, or 2/3. And then the probability of not getting an odd number. So now we want to count up how many faces are there that don't have odd numbers. And since 4 of the 6 faces did have odd numbers, that leaves 2 of the 6 faces that don't have odd numbers. So that probability is 2, 6, or 1/3. For number 17, it says a card is drawn from a standard deck of cards. We want to find the probability of A union B for each part. And we've got the little picture that shows us the different cards in a deck. Part A, event A is the event of getting a black card, and event B is the event of getting a heart. So the probability of A union B is the probability of getting a black card or a heart. And so we're going to count how many cards are there that are black or hearts out of the total. There are 52 cards in a deck, and 39 of them are black or hearts. And so we get the probability 39 out of 52, which reduces down to 3/4. For part B, event A is getting a diamond, and event B is getting an ace. So we want to count up how many cards are either a diamond or an ace. So the probability of A union B is getting a diamond or an ace. So we want to count how many cards are there that are diamonds or aces out of the total 52. There are 13 diamonds, and then there are 3 more aces. So that gives us 16 out of 52, which reduces down to 4/13. And then part C is the event A is getting a face card, and event B is getting a spade. So the probability A union B is the event of getting a face card or a spade. Remember the face cards, those are the jacks, the queens, and the kings. So we want to count the number of cards that are face cards or spades. So spades, there are 13 spades, and then we count This jack, that gets us 14, this queen, this king, so that was 14, 15, 16. This jack, 17, queen 18, king 19. And then this jack is number 20, queen is 21, and king is 22. So there's 22 cards out of 52, which reduces down to 11 out of 26. Part D is getting a face card. I'm sorry, part D, event A is getting a face card and event B is getting a 7. So the probability A union B is the probability of getting a face card or a 7. And there are 12 face cards and 4 7s. So that's going to be the number of cards that are face cards or 7s, which gives us 16. That's the 12 face cards plus the 4 7s. So we have 16 out of 52, or 4/13. Next, we'll look at problem number 18. It says, with the spinner from example 11.2 part C. So that's just this spinner. It has 4 sections that are blue, red, yellow, and green. We're going to spin twice and record the color on each spin. So for this experiment, consider the sample space and the following events. So the sample space is actually given to us right here. So this is getting red on both spins. This is first spinning red and then yellow. This is first spinning red and then green. This is first red and then blue, and so on. So event A is that we get a green on the first spin. So that is right here where our first spin is green, and event B is getting a yellow on the second spin. And so notice there is an overlap where we get green on the first and yellow on the second. A union B is that we get a green on the first spin or a yellow on the second. And remember, when we do union, we're always saying or both. So GY, green on the first and yellow on the second, is included in A union B. It says verify the following. First, that the number of elements in the sample space is 16. So I just listed out the sample space, which is just these 16 different things that can happen. And we can see there's 4 columns and 4 rows. So there will be 16 different outcomes in the sample space. The number of elements in event A is 4. So remember, event A was that we spun and we got a green on the first spin. So there are 4 different outcomes in that event. The number of elements in event B is 4. Event B was that we got a yellow on the second spin, and there are 4 different outcomes in that event. The number of elements in A union B is 7, and we can count there are in fact 7 different outcomes. The number of outcomes in A intersect B is 1. A intersect B means that both things happen. So we got green on the first spin and yellow on the second spin. And yeah, there is only one way to do that. That's the GY. Okay. The number of outcomes, I'm a little confused about that, in A is equal to 1. I think we should skip that. The number of outcomes in event A is 4. We already said that up above. The probability of event A happening is 4 out of 16. It's just the number of elements in outcome A divided by the number of elements in the sample space, and that's 4 out of 16. The probability that event B happens is also 4 out of 16, and that's the number of outcomes in event B divided by the number of outcomes in the sample space, and that is 4 out of 16. The probability of A union B is 7 out of 16. So to find the probability of A union B, we would find the number of outcomes in A union B divided by the number of outcomes in the sample space. And up above, we saw that the number of outcomes in A union B was 7, and we know the number of outcomes in the sample space is 16. And then the probability of A intersect B is 1 out of 16. To find that probability, we first look at the number of outcomes in A intersect B, which we know from previous is 1, and that's divided by the number of outcomes in the sample space, which is 1 out of 16. Okay, so this is a very long problem. It says show that the probability of A union B is equal to the probability of A plus the probability of B minus the probability of A intersect B. Okay, so we know the probability of A union B. That was 7 out of 16, and that is equal to 4/16 plus 4/16 minus 1/16. So it works out. And this formula is going to always work out. The probability of the union of two events will always equal the probability of the first event plus the probability of the second event minus the probability of their intersection. Okay, and so we have shown that this really does work. And then it says apply this to find the probability of A union B in the following cases. Event A is the event where we get a red on the first spin, so that's going to be this first column. Event B is the probability of getting the same color on both spins. So that's going to be that we get a red and a red, or a yellow and a yellow, or a green and a green, or a blue and a blue. So the probability of event A, the probability of getting a red on the first spin, is the probability that we get red, 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 yellow, red, green, or red, blue. There's 4 different outcomes out of the 16 in the sample space. The probability for B, which is the probability of getting the same color on both spins, is the probability of getting red, red, yellow, yellow, green, green, or blue, blue. And that's going to be 4 out of 16 because there's 4 outcomes in the event and 16 outcomes in the sample space. And the probability for their intersection is the probability of getting a red on the first spin and the same color on both spins. So the only way that that can happen is if both spins give us a red. That has a probability of 1 out of 16. To find the probability of the union, that's going to be the probability of getting a red on the first spin or getting the same color on both spins. We can use the formula, the probability of A plus the probability of B minus the probability of their intersection. So that's 4/16 plus 4/16 minus 1/16. If we add the first 2 fractions, we get 8/16, and then we subtract 1/16, and that gives us 7/16. Okay, and then we're going to take a look at another couple events. Event A is that we get a yellow or a blue on the first spin. So we can get a yellow on our first spin or a blue. And event B is the event that we get a red or a green on the second spin. So getting a red or green on the second spin. So this is how to get a red on the second spin, and then this row will be a green on the second spin. So we first find the probability of event A, the probability of getting a yellow or blue on the first spin. And I've listed out the possibilities. There are 8 of them. And so that probability is 8 out of 16. And I've reduced that down to 2/4. We also could reduce it to 1/2. Event B has a probability. So this is the probability of getting a red or a green on the second spin. I've listed those possibilities out, and that's also equal to 8/16, which I've reduced to 2/4. We could also reduce it to 1/2. A intersect B, we want to find the probability of getting either a yellow or a blue on the first spin and getting a red or green on the second spin. So we could get a yellow on the first spin and a red on the second. We could get blue on the first spin and red on the second. We could get yellow on the first spin and green on the second, or blue on the first spin and green on the second. So there's 4 different outcomes out of the 16 outcomes, and that reduces down to 1/4. Next, I'm going to find the probability of A union B. So this is getting a yellow or blue on the first spin, or a red or green on the second spin. We can use the formula, the probability of A plus the probability of B minus the probability of their intersection. So I have 2/4 plus 2/4 minus 1/4. Okay, if I add the first 2 fractions, I get 4/4, and then I'm going to subtract 1/4, and that gives me 3/4. Okay, number 19 says, for the experiment in exercise number 18, where a spinner is spun twice, consider the following events. So we're still looking at the same idea. Event A is getting a blue on the first spin. So that's going to be this column. Event B is getting a yellow on one spin. Event C is getting the same color on both spins. Describe the following events and find their probabilities. A union B, getting a blue on the first spin or a yellow on one spin. So I could have a blue and then a red, blue and then yellow, blue and then green, or blue and then blue. I could have yellow and then red. Now, when it says getting a yellow on one spin, I assume they mean at least one spin, but that's something that could be clarified a little bit better, whether they mean yellow on only one or at least one. But I went ahead and included 2 yellows. And then I have yellow and then green, yellow and then blue, yellow and then red, or green and then yellow. So to find that probability, I count how many outcomes are there out of the 16 outcomes in the sample space, and that gives me 5/8. Part B, we want to think about the event B intersects C, and this is getting a yellow on one spin and getting the same color on both spins. There's only one way for that to happen, which is that both spins are yellow. And so that probability is 1/16. Part C, B complement. So B was getting a yellow on a spin. The complement of that would be not getting yellow on either spin. So I've listed out the ways of not getting yellow on either spin. And its probability is 9/16 because there's 9 outcomes in that event. So one thing I want to look at is the fact that the probability of B complement is equal to 1 minus the probability of B. Because there were 7 different ways to get yellow on at least one spin. Oh, you're not seeing the PowerPoint. Oh, okay, give me just a second. Thank you for letting me know. Oh, now you're seeing it. Okay, all right. Okay, so let me see if I can count the 7 different outcomes where we have yellow on at least one. So here's 1, 2, 3, 4, 5, 6, 7. So the probability of B complement is equal to 1 minus the probability of B. Okay, and so that brings us to some different properties about probabilities. For any event, the probability of the event is going to be a number between 0 and 1. It could equal 0 or it could equal 1, but it can never be negative and it can never be bigger than 1. The probability of the empty set is equal to 0. There is no way for that to happen if there are no outcomes in the event. And the probability of the sample space is equal to 1. For any events A and B, the probability of A union B is equal to the probability of A plus the probability of B minus the probability of their intersection. And if A with a line over it means the complement of event A, then the probability of A complement is always equal to 1 minus the probability of A. So next we're going to look at problem number 20. It says a student is selected at random. Let A be the event that the selected student is a sophomore, and B be the event that the selected student is taking English. Write in words what is meant by each of the following probabilities. The probability of A union B. That's the probability that the selected student is a sophomore or taking English, or both. Okay, whenever we do unions, we're going to include the idea of both events. The probability of A intersect B is the probability that the selected student is a sophomore who's taking English. So 1 minus the probability of A. We know that 1 minus the probability of A is the probability of A complement. And A complement is the event that the student isn't a sophomore. So 1 minus the probability of A is the probability of A complement, and so that's the probability that the student is not a sophomore. Number 21 says, what is false about the following statements? Part A, the probability that it will rain today is 20%, and the probability that it won't rain today is 60%. Okay, the sample space is all the possible outcomes, which is it rains or it doesn't rain. Those are the 2 outcomes. And we know the probability of the sample space has to equal 1. So if we add up 20% and 60%, we're supposed to get 1. But 20% plus 60% equals 80%, which is not 1. Part B, it says, since a deck of cards contains some face cards and some non-face cards, the probability of drawing a face card is 1/2. Okay. If there's only 2 outcomes, the probability of each outcome is 1/2, but only if each outcome is equally likely. Okay, and I don't think these two outcomes are equally likely. There are many more non-face cards than face cards, so the outcomes are not equally likely. Part C, the probability that I get an A in this course is 1.5. All probabilities have to be between 0 and 1. You can never have a probability that's larger than 1. Let's take a look at number 22. It says 2 fair 6-sided dice are rolled and the sum of the dots on the top face is recorded. Well, part A was to complete the table showing the number of ways that each sum can occur. There's only one way to get a sum of 2. There's 2 ways to get a sum of 3. There are 3 different ways to get a sum of 4. Okay, we can just take a look at this picture from your book, and it shows us the number of ways to get each sum. The only one way to get a sum of 12 is to get a 6 and a 6. Part B says to use the table to find the probability of each of the following events. Event A is that the sum is prime. So if the sum is prime, that means it needs to be 2, 3, 5, 7, or 11. There are 36 different possibilities down here. One of those has a sum of 2, 2 ways to get a sum of 3. There's 4 ways to get a sum of 5. There are 6 ways to get a sum of 7. And then there's 2 ways to get a sum of 11. So this gives us 15 different ways to get a sum that's prime out of 36, and that reduces down to 5 out of 12. Part B is having the sum be a divisor of 12. So if the sum is a divisor of 12, that means the sum is 2, 3, 6, or 12. And there's 1 way to get a sum of 2, 2 ways to get a sum of 3, there's 5 ways to get a sum of 6, and 1 way to get a sum of 12. So there's 9 ways to get the sum being a divisor of 12, and that reduces to 1 out of 4. Part C, the sum is a power of 2. The powers of 2 that we could get are 2, 4, and 8. There's only 1 way to get a sum of 2, 3 ways to get a sum of 4, and 5 ways to get a sum of 8. So there's 9 ways to get a sum that's a power of 2. And so the probability is 9 out of 36, which reduces down to 1 out of 4. Part D, the sum is greater than 3. Well, if the sum is greater than 3, then the sum must be 4, 5, 6, 7, 8, 9, 10, 11, or 12. And so I added up the ways to get those sums. That came out to be 33 different ways out of 36, which is 11 out of 12. We could have also used the complement, and the complement would be that the sum isn't greater than 3. So in other words, the sum is less than or equal to 3. And so there are 3 ways to get a sum that's less than or equal to 3. So we could have done 1 minus 336. Next, we'll look at number 23. It says the probability of a geometric event involving the concept of measure, length, area, or volume is determined as follows. Let M of A and M of S represent the measures of event A and the sample space S. Then the probability of event A is the measure of A divided by the measure of S. For example, in the first picture, If the length of S is 12 centimeters and the length of A is 4 centimeters, then the probability of A would be 4/12 or 1/3. In the second figure, if the area of region B is 10 square centimeters and the area of region S is 60 square centimeters, then the probability of event B would be 10/60 or 1/6. And then it says a bus travels from Albany to Binghamton, a distance of 100 miles. If the bus has broken down, we want to find the probability that it has broken down within 10 miles of either city. Part A, the road from Albany to Binghamton is the sample space. What is M of S? M of S is the total distance, the 100 miles. Part B, event A is that part of the road within 10 miles of either city. What is M of A? That would be 20 miles, okay? 10 miles from Albany and 10 miles from Binghamton. And then we're going to find the probability of A. The probability of A would be M of A divided by M of S, and that's 20 miles divided by 100, which is 20% or 1/5. 11.1, number 24, it says the dartboard illustrated is made up of circles with radii 1, 2, 3, and 4 units. A dart hits the target randomly. What is the probability that the dart hits the bullseye? And it gives us a hint about finding the area of a circle. So I'm going to assume that it's going to hit somewhere in one of these circles. So M of S is the area of the entire thing, which is 16 pi. A is the event of hitting the bullseye. M of A is just the area of the smallest circle, which would be 1 pi. And then the probability of event A is M of A divided by M of S, and that's 1 pi out of 16 pi. And that reduces down to 1/16. Did anybody have any questions about anything? Okay. Well, if nobody has any questions, I think we'll go ahead and end our meeting. We are not going to have a session tomorrow or on the weekend, so I will see you here again on Monday. Please feel free to send me an email if you have any questions about anything. See you on Monday.